charging of objects by rubbing with a dry cloth. When certain materials, such as glass, perspex, or polythene, are rubbed with a dry cloth, they can become charged. This phenomenon is known as charging by friction and can be explained in terms of electron transfer through friction. When two different materials are rubbed together, the outermost electrons of one material can be transferred to the other material. This transfer occurs because different materials have different tendencies to attract and hold electrons. The material with a higher affinity for electrons tends to gain electrons and become negatively charged, while the material with a lower affinity loses electrons and becomes positively charged. For example, when a glass rod is rubbed with a dry cloth, some electrons from the glass are transferred to the cloth. The glass rod becomes positively charged as it loses electrons, charging occurs and the cloth becomes negatively charged as it gains electrons. To demonstrate the process of charged glass rod attracts the paper pieces or bends the water stream, take a glass rod and rub it vigorously with a dry cloth. Then this activity illustrates the transfer of electrons by friction and the subsequent charging of objects. 1.2 Forces between electric charges. Electric charges exert forces on each other due to their fundamental property. These forces can be described by Coulomb's law, which states that the force between two charges is directly proportional to the product of their magnitudes and inversely proportional to the square of the distance between them. Like charges, charges with the same sign, either both positive or both negative, repel each other, while unlike charges, charges with opposite signs attract each other. This observation demonstrates the fundamental property of electric charges. To demonstrate this, you can perform a simple activity. Take two balloons and rub them against your hair or a woolen cloth to charge them. The charged balloons will have the same type of charge, either positive or negative. Bring the balloons close to each other without touching them. You will observe that they repel each other, showing the repulsive force between like charges. Next, charge another balloon, and bring it close to the charged balloons. You will observe that the charged balloons attract the newly charged balloon, indicating the attractive force between unlike charges. By using measurement and observation, along with logical reasoning, you can further explore and analyze the forces exerted by electric charges. 1.3 Charging by induction. Charging by induction is a process that involves a charged object attracting objects with zero net charge. This method of charging relies on the redistribution of charges in objects through the influence of a charged object. To demonstrate charging by induction, you can perform a simple experiment. Start with two objects, one charged and one uncharged. Let's take a neutral metal sphere and a negatively charged balloon. Bring the charged balloon close to the metal sphere without touching it. Due to the presence of the negatively charged balloon, the electrons in the metal sphere will be repelled. The electrons in the metal sphere will redistribute, with some moving away from the balloon's influence and others moving towards it. As a result, the side of the metal sphere closer to the balloon becomes positively charged, while the side farther away becomes negatively charged. Now, if you bring a neutral object, such as a small piece of paper, close to the charged metal sphere, you will observe that the paper is attracted to the metal sphere. This attraction occurs because the positively charged side of the metal sphere induces a separation of charges in the neutral object, attracting the opposite charges towards it. Charging by induction demonstrates the ability of charged objects to attract objects with zero net charge through the redistribution of charges. 1.4 Electric fields and field lines. An electric field is a region in which an electric charge experiences a force due to the presence of other charges. It can be represented by electric field lines, which depict the direction and strength of the electric field. The electric field lines around a positive point charge radiate outward, indicating the direction in which a positive test charge would move if placed in the field. Conversely, the electric field lines around a negative point charge converge inward, representing the direction of the force on a positive test charge. The density of the line signifies the strength of the electric field, with closely spaced lines indicating a stronger field. When two or more charges are present, the electric field lines interact and combine. For example, the electric field lines between two positive charges would be repulsive, as they push away from each other. On the other hand, the electric field lines between a positive and a negative charge would be attractive, as they converge towards each other. In the case of charged parallel plates, the electric field lines are uniform and parallel between the plates. The field lines originate from the positive plate and terminate on the negative plate. This configuration creates a constant electric field between the plates. Compared to other force fields, such as gravitational and magnetic fields, electric fields have unique properties. While gravitational fields are always attractive and act on mass, and magnetic fields are generated by moving charges or current. Carrying conductors, electric fields can be either attractive or repulsive and act on electric charges. Electric fields can also be shielded by conducting materials, unlike gravitational and magnetic fields. Understanding electric fields and their representation through field lines requires skills in algebra and computation to analyze the forces experienced by charged objects within these fields. 1.5 Hazards and useful applications of static charge. Static charge, or static electricity, can present both hazards and useful applications in various situations. Here are examples of one hazard and one useful application. Hazard: lightning strikes. Lightning is a natural occurrence that involves the discharge of static electricity between the atmosphere and the ground or between different parts of the atmosphere. Lightning strikes can cause significant damage to property, pose a threat to human life, and lead to forest fires. It is essential to take precautions during thunderstorms and avoid being outdoors in open areas. Useful application: electrostatic painting. Electrostatic painting is a technique used to apply paint to objects with a uniform and controlled coating. The object to be painted is given an electric charge, while the paint particles are charged with the opposite polarity. The charged paint particles are attracted to the grounded object, creating an even and efficient paint coating. This method is widely used in industries such as automotive, furniture, and appliance manufacturing. It is important to note that the presence of a charged ionized atmosphere, such as in areas with high humidity or industrial processes, can affect the behavior of static charges. The ionized atmosphere can enhance or inhibit the accumulation and dissipation of static charge, leading to different outcomes in various situations. Current electricity. 2.1 Conductors and insulators are two different types of materials that exhibit distinct properties when it comes to the flow of electric current. Conductors are materials that allow the flow of electric current through them easily. They have properties that facilitate the movement of charged particles, such as electrons. In conductors, electrons are loosely bound to their atoms, allowing them to move freely in response to an electric field. Metals are excellent conductors of electricity due to the presence of free electrons in their atomic structure. Other materials, such as certain types of solutions or gases, can also act as conductors under specific conditions. Insulators, on the other hand, are materials that impede or prevent the flow of electric current. They have properties that restrict the movement of charged particles. In insulators, electrons are tightly bound to their atoms and cannot move as freely as in conductors. This makes insulators poor conductors of electricity. Examples of insulating materials include rubber, plastic, glass, and ceramic. To differentiate between conductors and insulators, a low-voltage test circuit with lamp indicator can be used. When a conductor is connected to the circuit, the lamp will light up, indicating the flow of electric current. In contrast, when an insulator is connected, the lamp will not light up, indicating the absence of current flow. This experiment demonstrates the different electrical properties of conductors and insulators and their ability to allow or hinder the flow of electric current. The electron properties of metals and nonmetals in chemistry play a crucial role in distinguishing between conductors and insulators. Metals have a relatively large number of free electrons due to their atomic structure, which allows them to conduct electricity effectively. In contrast, nonmetals have a smaller number of free electrons, making them poor conductors of electricity. This distinction is related to the arrangement of electrons in the valence shell of atoms and the ease with which they can be excited and participate in electrical conduction. 2.2 An electric current in a metal primarily consists of the flow of electrons. Metals, due to their atomic structure, have a large number of free electrons in their valence shells. When a potential difference is applied across a metal, these free electrons move in response to the electric field, creating an electric current. This flow of electrons is responsible for the conductivity of metals and their widespread use in electrical systems. In other conducting media, such as electrolytes and semiconductors, the movement of both negative and positive charge carriers contributes to the electric current. In electrolytes, the electric current involves the movement of ions, which are atoms or molecules with a net electric charge. This movement occurs due to the presence of an electric field or a potential difference. Semiconductors, like metals, also involve the flow of electrons as the primary charge carriers. However, in semiconductors, the flow of electric current can be modulated by varying external factors such as temperature or impurities, giving them unique electrical properties. Semiconductors find extensive applications in electronic devices, where their ability to control and manipulate current flow is leveraged. Electrolytes play a vital role in batteries by enabling the movement of ions between electrodes, allowing the flow of electric current and the conversion of chemical energy into electrical energy. Semiconductors, on the other hand, are essential in the construction of various electronic components, such as transistors, diodes, and integrated circuits, which form the backbone of modern electronics. The properties of metals and nonmetals in chemistry are significant in understanding the behavior of these materials as conductors or insulators. Metals, as mentioned earlier, have a large number of free electrons, making them excellent conductors. Nonmetals, on the other hand, have fewer free electrons and typically form covalent or ionic bonds, which restrict the movement of electrons, and make them insulators or poor conductors of electricity. 2.3 Electron flow and conventional current are two different ways to describe the movement of electric charge in a circuit. Electron flow refers to the movement of electrons, which are negatively charged particles, through a conductor in response to an electric field. In this convention, electrons flow from the negative terminal of a power source, such as a battery, toward the positive terminal. This convention aligns with the actual movement of electrons, as they are negatively charged and repelled by the negative terminal while attracted to the positive terminal. On the other hand, conventional current is a historical convention that describes the movement of positive charges, or holes, in the opposite direction. According to the conventional current convention, current flows from the positive terminal of a power source to the negative terminal. This convention was established before the discovery of the electron and was based on observations of the flow of current in conductive solutions. While both conventions describe the same phenomenon of current flow, they differ in the direction attributed to the movement of charge carriers. In modern physics and electronics, electron flow is the convention commonly used, as it aligns with the behavior of negatively charged electrons in most conductors. 2. For the unit of electrical current is the Ampere. It is named after the French physicist André-Marie Ampere, who made significant contributions to the understanding of electromagnetism. The Ampere is defined as 1 coulomb of electric charge flowing per second. In other words, if a charge of 1 coulomb passes through a point in a circuit in 1 second, the current is 1 ampere. 2.5 The relationship between charge, Q, current, I, and time, T, is given by the equation Q equals it. This equation states that the charge passing through a point in a circuit is equal to the product of the current flowing through it and the time for which the current flows. The unit of charge is the coulomb, C, and the unit of current is the ampere, A. Therefore, if the current is measured in amperes and the time in seconds, the resulting charge will be in coulombs. This equation is fundamental in understanding the flow of electric charge and is commonly used in calculations involving current, charge, and time. 2.6 Direct and alternating currents are two different types of electrical currents. Direct current, DC, is the type of current that flows continuously in one direction. In a DC circuit, the electric charge flows from the positive terminal of a power source to the negative terminal, maintaining a constant direction. Batteries and solar cells are examples of devices that provide DC power. In direct current systems, the current time graph appears as a straight line with a constant value. Alternating current, AC, on the other hand, periodically reverses its direction of flow. In an AC circuit, the electric charge alternates back and forth, changing its direction multiple times per second. AC is the type of current used for delivering electrical power to homes, businesses, and industries. The current time graph of an AC system appears as a waveform, typically a sine wave, with continuous oscillation between positive and negative values. The direction reversal in AC current allows for efficient transmission of electrical energy over long distances and enables the use of transformers to step up or step down voltage levels. In contrast, DC power is generally used for low voltage applications or devices that require a steady and unidirectional flow of current. 1, 2, 3, 4. 2.7 The period, T, and frequency, F, of alternating currents or voltages can be deduced by analyzing current time or voltage time graphs. The period, T, represents the time taken for one complete cycle of the alternating current or voltage waveform. It is measured in seconds. The frequency, F, represents the number of cycles per second and is measured in Hertz Hz. The relationship between period and frequency is given by the equation F equals 1T, where F is the frequency and T is the period. To determine the period and frequency from a current time or voltage time graph, one can measure the time interval between two corresponding points on the waveform. The time interval between any two identical points on the waveform, such as two consecutive peaks or zero crossings, represents the period. The reciprocal of the period gives the frequency. Mathematics skills in algebra and computation are necessary for performing calculations involving period, frequency, and their reciprocal relationship. Understanding the concept of period and frequency is important in various applications, such as electrical power generation, transmission, and signal processing. Electrical quantities 3.1 Conversion of electrical energy to other forms and vice versa. The conversion of electrical energy to other forms and vice versa is a fundamental concept in energy transformation. Here are some examples of these conversions. Electrical energy to light energy. One common example is the conversion of electrical energy to light energy in an incandescent lamp. When current passes through the filament of the lamp, it heats up and emits light. This is an example of electrical energy being converted into light energy. Electrical energy to mechanical energy. Electric motors are devices that convert electrical energy into mechanical energy. When an electric current flows through the motor, it creates a magnetic field that interacts with the field generated by permanent magnets, resulting in the rotation of a shaft. This rotation represents the conversion of electrical energy to mechanical energy. Electrical energy to thermal energy. Electrical heaters, such as electric stoves or electric water heaters, convert electrical energy into thermal energy. The electric current flowing through a resistive element generates heat, which warms up the surrounding environment or a specific medium. Electrical energy to chemical energy. Electrolysis is a process that converts electrical energy into chemical energy. It involves the decomposition of a compound, usually through the passage of an electric current, resulting in the separation of its constituent elements or ions. For example, during electrolysis of water, electrical energy can be used to split water molecules into hydrogen and oxygen gases. These examples demonstrate various energy conversions in the laboratory and everyday life, showcasing the versatility and applicability of electrical energy in different forms. 3.2 Relationship between V equals EQ. The relationship V equals EQ represents the equation for voltage, where V is voltage, E is energy, and Q is charge. Understanding the definitions of these terms and their units is crucial for applying this relationship effectively. Voltage, V, is the electric potential difference between 2 points and is measured in volts. V. It represents the amount of energy per unit charge required to move a charge from one point to another. Energy, E, is the capacity to do work or transfer heat and is measured in joules. J. In the context of this equation, it refers to the electrical energy associated with the movement of charges. Charge, Q, is the fundamental property of matter responsible for electrical phenomena and is measured in coulombs. C. It represents the amount of electric charge passing through a point in an electrical circuit. The relationship V equals EQ indicates that voltage, V, is equal to the energy, E, divided by the charge, Q. This equation demonstrates how the voltage across a component or circuit relates to the amount of electrical energy transferred per unit charge. To apply this relationship, you can use algebraic manipulations to rearrange the equation to solve for any of the variables, V, E, or Q, if the values of the other two variables are known. 3.3 Relationship between P equals 4 and P equals ET. The relationship P equals 4 and P equals ET are both equations related to power in electrical circuits. However, they have different forms and units. In the equation P equals 4, P represents power, I represents current, and V represents voltage. This equation states that power, P, is equal to the product of current, I, and voltage, V. Power is measured in watts, W, current in amperes, A, and voltage in volts, V. On the other hand, the equation P equals ET relates power, P, to energy, E, and time, T. It states that power is equal to the energy transferred, E, divided by the time taken, T. The unit of power, P, remains watts, W, but energy, E, is measured in joules, J, and time, T, is measured in seconds, S. The consistency of units in both equations is maintained because power is defined as the rate at which energy is transferred or work is done. The equation P equals 4 represents power as the product of current and voltage, indicating the rate at which electrical energy is being transferred or used in a circuit. Similarly, the equation P equals ET relates power to the rate at which energy is transferred over a specific period. While both equations calculate power, they are applicable in different contexts. P equals 4 is often used when the voltage and current values of a circuit are known, whereas P equals ET is useful when the energy and time values are available. 1, 2, 3, 4, 5, 6. 3.4 Importance of conserving electrical energy and means of doing so. Conserving electrical energy is crucial for several reasons, including the limited reserves of fossil fuels, the need to reduce greenhouse gas emissions, and the importance of energy efficiency. Here are some means of conserving electrical energy. Use energy-efficient lighting. Replacing traditional incandescent lamps with energy-efficient alternatives like fluorescent lamps or LED bulbs can significantly reduce energy consumption for lighting purposes. These alternatives convert a higher percentage of electrical energy into light while producing less heat. Opt for energy-efficient appliances. Choosing appliances with high energy efficiency ratings can lead to significant energy savings. Energy-efficient refrigerators, air conditioning units, washing machines, and other appliances utilize advanced technologies to minimize energy wastage and operate more efficiently. Embrace renewable energy sources. Utilizing renewable energy sources, such as solar power, wind energy, or hydroelectric power can help conserve electrical energy and reduce dependence on fossil fuels. Installing solar panels or wind turbines enables the generation of electricity from clean and sustainable sources. Practice smart energy management. Implementing energy management strategies like turning off lights and appliances when not in use, using programmable thermostats, and optimizing energy usage in industrial processes can result in substantial energy savings. These practices involve conscious efforts to reduce unnecessary energy consumption. Insulate buildings and improve energy efficiency. Proper insulation of buildings helps reduce heat transfer and minimizes the need for excessive heating or cooling. Enhancing insulation, sealing air leaks, and using energy-efficient windows and doors contribute to overall energy conservation. Promote energy awareness and education, educating individuals about the importance of conserving electrical energy and raising awareness about energy-efficient practices can have a significant impact. Encouraging energy-saving habits and providing information on available resources and incentives can empower people to make informed decisions. Conserving electrical energy not only reduces energy costs but also contributes to the preservation of natural resources, minimizes environmental impact, and helps ensure a sustainable energy future. Considering the chemistry and biology related to the burning of hydrocarbons and the ecological consequences, energy conservation becomes even more imperative for mitigating climate change and promoting environmental well-being. Overall, adopting energy-efficient technologies and practices, utilizing renewable energy sources, and fostering a culture of energy conservation are essential steps toward a more sustainable and responsible energy consumption pattern. Circuit and component circuit diagrams. When it comes to constructing circuit diagrams, students can refer to a list of graphical symbols for guidance. Circuit diagrams are visual representations of electrical circuits that use abstract, standardized symbols and lines to depict the components and connections within the circuit. These symbols include shapes such as rectangles, circles, lines, and arrows, which represent basic electrical components like resistors, capacitors, and transistors. By understanding these symbols, students can effectively communicate and interpret circuit diagrams. Differentiating series and parallel circuits. To understand the difference between series and parallel circuits, students can consider the arrangement of components and their polarity. In a series circuit, components are connected in a line, end-to-end, with the positive terminal of one component connected to the negative terminal of the next component. The total resistance in a series circuit is the sum of individual resistances, and the current remains the same throughout the circuit. In contrast, in a parallel circuit, components have their terminals connected separately to the positive and negative sides of the power supply. The total resistance in a parallel circuit can be calculated using the formula 1Rp equals 1R1 plus 1R2 plus 1R3. Where Rp represents the total resistance and R1, R2, R3, etc. represent the individual resistances. In a parallel circuit, the voltage across each component is the same, while the total current is the sum of the currents flowing through each branch. For practical activities, students can set up simple circuits given a circuit diagram, paying attention to the polarity and suitability of components. By working with series circuits that include diodes, resistors, and instruments, students can gain hands-on experience and further understand the characteristics and behavior of series circuits. Cells, to explain the functions of the various parts of a zinc-carbon cell and discuss its components functions, students can draw a diagram of a zinc-carbon cell. A zinc-carbon cell, also known as a dry cell or Leclanche cell, consists of a zinc anode, a carbon cathode, and a moist paste of ammonium chloride, NH4Cl, electrolyte. The zinc anode serves as the negative terminal and provides electrons, while the carbon cathode acts as the positive terminal and accepts electrons during the electrochemical reaction. The ammonium chloride electrolyte facilitates the flow of ions between the anode and cathode, allowing the cell to generate an electric potential difference. Other types of primary cells include alkaline cells, lithium cells, and silver oxide cells, each with their own construction and chemistry. To distinguish between primary and secondary cells, students can compare characteristics such as terminal voltage, maximum current, internal resistance, portability, and rechargeability. Primary cells are non-rechargeable and have a relatively stable terminal voltage, while secondary cells are rechargeable and can be reused multiple times. Secondary cells have a higher maximum current output and a lower internal resistance compared to primary cells. However, secondary cells are often less portable due to their larger size and weight. For understanding how a secondary cell can be recharged, students can draw a circuit diagram considering the polarity and charging voltage. Recharging a secondary cell involves connecting it to an external power source with a voltage higher than the cell's terminal voltage. The positive terminal of the power source is connected to the positive terminal of the cell, and the negative terminal of the power source is connected to the negative terminal of the cell. This arrangement allows the current to flow in the opposite direction, reversing the chemical reactions that occur during discharge and restoring the cell's stored energy. IV relationships, to investigate the relationship between current and potential difference in various scenarios, students can conduct experiments with different materials and components. For metallic conductors at a constant temperature, the current flowing through the conductor is directly proportional to the potential difference applied across it. This relationship is known as Ohm's law, where resistance, R, is the ratio of potential difference, V, to current, I equals VR. By varying the potential difference and measuring the resulting current, students can plot IV graphs and draw appropriate conclusions about the conductor's resistance. Similar experiments can be performed with filament lamps, semiconductor diodes, and solutions of copper sulfate in water using copper electrodes. These experiments allow students to observe how different materials and components exhibit varying IV relationships. For example, filament lamps show a nonlinear IV relationship, while diodes exhibit a nonlinear relationship with a threshold voltage. Before conducting, solutions of copper sulfate in water with copper electrodes demonstrate the electrolytic properties and the changes in resistance with varying potential differences. Resistance, to explain the concept of resistance, students can understand that resistance is a property that opposes the flow of electric current. It can be thought of as the friction experienced by electrons as they move through a material. Resistance can vary with the current in some cases, such as in devices like thermistors or light-dependent resistors, where the resistance changes with temperature or light intensity, respectively. Students can apply Ohm's law, I equals VR, to relate current, potential difference, and resistance. This equation states that the current flowing through a conductor is directly proportional to the potential difference across it and inversely proportional to the resistance of the conductor. An ammeter needs to have a very low resistance to minimize its impact on the circuit being measured. A low-resistance ammeter ensures that the current being measured is not significantly affected or diverted by the presence of the ammeter itself. On the other hand, a voltmeter needs to have a very high resistance to minimize the current flowing through it when measuring potential difference. A high-resistance voltmeter prevents a significant amount of current from flowing through the voltmeter, ensuring accurate voltage measurements. To solve problems involving series and parallel resistance, students can use appropriate formulas. For resistors in series, the total resistance, Rs, is the sum of the individual resistances, Rs equals a 1 plus a 2 plus a 3. For resistors in parallel, the reciprocal of the total resistance, 1 Rp, is the sum of the reciprocals of the individual resistances, 1 Rp equals 1 or 1 plus 1 or 2 plus 1 or 3. By applying these formulas, students can calculate the equivalent resistance in various circuit configurations. Electricity in the home. The parallel connection of domestic appliances is preferred for several reasons. In a parallel circuit, each appliance is connected individually to the power supply, allowing them to operate independently. If one appliance fails or is disconnected, the others can continue to function. Additionally, each appliance receives the same voltage, ensuring consistent operation and preventing one appliance from affecting others in terms of voltage fluctuations or power loss. A fuse or circuit breaker serves as a protective device in electrical circuits. They are designed to interrupt the flow of current in the event of an overload or short circuit, preventing damage to the wiring and appliances, as well as reducing the risk of fire. The earth wire, also known as the grounding wire, provides a path for current to safely flow into the ground in the case of a fault, further enhancing electrical safety. When selecting a fuse or circuit breaker for a given appliance, students should consider the current rating of the appliance. The current rating of the protective device should be equal to or slightly higher than the maximum current the appliance is expected to draw. This ensures that the protective device will trip or blow if the current exceeds safe limits, safeguarding the circuit and appliances from potential damage or hazards. Connecting electrical appliances to incorrect or fluctuating voltage supplies can have adverse effects. Appliances designed for a specific voltage may not function correctly or may be damaged if connected to a higher or lower voltage. Fluctuating voltages can cause fluctuations in power supply, leading to inconsistent operation, decreased efficiency, and potential damage to the appliances. It is essential to use voltage supplies within the specified range to ensure the safe and optimal performance of electrical appliances. Electronic semiconductor diode and half-wave rectification. A semiconductor diode can be used in half-wave rectification, which is a process of converting alternating current, AC, to direct current, DC. In this process, a diode allows the flow of current in only one direction, blocking the reverse flow. When the AC signal is applied to the input of a half-wave rectifier circuit, the diode conducts current during the positive half cycle of the AC signal, allowing it to pass 1 through and become part of the output waveform. However, during the negative half cycle of the AC signal, the diode blocks the current, resulting in zero output. This effectively removes the negative half of the AC signal, leaving only the positive half in the output waveform. To illustrate this, let's consider the variation of voltage with time, Vt, graphs before and after rectification. Before rectification, the AC input waveform would typically be a sinusoidal waveform that alternates between positive and negative voltages. After rectification using a half-wave rectifier circuit, the negative half of the waveform is removed, resulting in a waveform that only contains the positive half. This can be seen in the Vt graph, where the negative voltage portion is completely eliminated, and the positive voltage portion remains unchanged. For a more visual representation, you can refer to the Vt graph provided in Reference 4. This graph shows the voltage waveform before and after half-wave rectification, clearly indicating the removal of the negative half of the AC signal. Differentiating direct current from batteries and rectified alternating current. Direct current, DC, obtained from batteries and rectified alternating current, AC, differ in their voltage time, Vt, characteristics. Let's consider the Vt graphs for both cases to understand their distinctions. Direct current from batteries provides a constant voltage over time. The Vt graph for DC from batteries would appear as a straight line parallel to the time axis, indicating a constant voltage value. Since batteries provide a steady flow of electrons in a single direction, the voltage remains constant, without any fluctuations or reversals. On the other hand, rectified alternating current, AC, is obtained by converting AC to DC using rectification techniques such as half-wave or full-wave rectification. In the case of half-wave rectification, as explained earlier, the negative half of the AC waveform is removed. The resulting Vt graph for rectified AC would show pulses or spikes of positive voltage corresponding to the positive half cycles of the AC signal, with zero voltage during the negative half cycles. However, it is important to note that the rectified AC waveform still contains some ripple or fluctuations, as it is not a perfectly smooth DC signal. To better understand the Vt graphs for both cases, you can refer to the references 4 and 5. These sources provide visual representations of the voltage waveforms before and after rectification, clearly highlighting the differences between direct current and rectified alternating current. Logic gates. Symbols for logic gates, limited to 2 input gates and gate. The symbol for an AND gate is a triangle shape with 2 inputs and 1 output. The inputs are represented by 2 lines converging into the triangle, and the output is represented by a single line coming out of the triangle. The symbol can vary slightly depending on the diagramming convention used. OR gate. The symbol for an OR gate is a shape with 2 inputs and 1 output. The inputs are represented by 2 lines entering the shape, and 2. The output is represented by a single line leaving the shape. Similar to the AND gate, the symbol may have slight variations depending on the diagramming convention. NOT gate. The symbol for a NOT gate, also known as an inverter, is a triangle with a small circle at its input side. The input is represented by a line entering the triangle, and the output is represented by a line leaving the triangle. NAND gate. The symbol for a NAND gate is a combination of the AND gate symbol and the NOT gate symbol. It consists of a triangle with 2 inputs and 1 output, and a small circle at the input side. NOR gate. The symbol for a NOR gate is a combination of the OR gate symbol and the NOT gate symbol. It consists of a shape with 2 inputs and 1 output, and a small circle at the input side. Function of each gate with truth tables. AND gate. The AND gate produces a high, or logic 1, output only when both of its inputs are high. Otherwise, it produces a low, or logic 0, output. The truth table for an AND gate is as follows: input A, input B, output 0000101001111. OR gate. The OR gate produces a high output if at least one of its inputs is high. It produces a low output only when both inputs are low. The truth table for an OR gate is as follows: input A, input B, output 0000111011111. NOT gate. The NOT gate, or inverter, produces the logical complement of its input. It inverts or flips the input signal. The truth table for a NOT gate is as follows: input output 0110. NAND gate. The NAND gate produces a high output unless both of its inputs are high. It produces a low output when both inputs are high. The truth table for a NAND gate is as follows: for input A, input B, output 001011 101 110. NOR gate. The NOR gate produces a high output only when both of its inputs are low. Otherwise, it produces a low output. The truth table for a NOR gate is as follows: input A, input B, output 001 010 100 110. Analysis of circuits involving combinations of no more than 3 logic gates. Circuits involving combinations of logic gates allow for more complex logical operations. By combining multiple gates, it is possible to create circuits that perform various logical functions and operations. When analyzing circuits with combinations of no more than 3 logic gates, it is essential to understand the behavior and truth tables of each gate involved. By connecting the outputs of one or more gates to the inputs of other gates, complex logical operations can be achieved. The outputs of one gate become inputs for subsequent gates, allowing for the creation of logical expressions and decision-making circuits. For example, a simple alarm circuit can be built using combinations of logic gates. By using input signals from sensors, such as a motion sensor or a door sensor, these signals can be fed into logic gates to determine the condition for activating an alarm. The output of the logic gates can then control the activation of an alarm device, such as a buzzer or a light. Impact of electronic and technological advances on society. Electronic and technological advances have had a significant impact on society, transforming various aspects of our lives. Some of the key impacts include communication. Advances in electronics and technology have revolutionized communication. The development of smartphones, the internet, and social media platforms has made communication faster, more convenient, and accessible to people worldwide. We can now easily connect with others, share information, and collaborate regardless of geographical boundaries. Automation and efficiency. Electronics and technology have automated many processes, increasing efficiency and productivity in various industries. Automation has led to improved manufacturing processes, streamlined operations, and reduced human error. Tasks that were once time-consuming and labor-intensive can now be accomplished with greater speed and accuracy. Healthcare. Electronics and technology have made significant contributions to healthcare. Medical devices and equipment, such as MRI machines, CT scanners, and pacemakers, have revolutionized diagnosis and treatment. Telemedicine has also become more prevalent, allowing patients to access healthcare remotely and receive consultations from specialists in different locations. Access to information. The internet and electronic devices have democratized access to information. People can now easily access vast amounts of knowledge, conduct research, and learn new skills online. This has led to greater educational opportunities and the ability to stay informed on a wide range of topics. Entertainment and media. Electronics and technology have transformed the entertainment and media industries. Streaming services, online gaming, virtual reality, and augmented reality have created immersive and interactive experiences for users. Digital media platforms have also changed the way we consume and share content, offering personalized recommendations and instant access to a wide variety of entertainment options. Environmental impact. Electronic and technological advances have both positive and negative environmental impacts. On one hand, energy-efficient devices, renewable energy technologies, and smart grids have the potential to reduce energy consumption and carbon emissions. On the other hand, the proliferation of electronic waste, e-waste, poses challenges in terms of disposal and recycling. Overall, the impact of electronic and technological advances on society is vast and multifaceted. It has transformed the way we communicate, work, access information, and entertain ourselves. However, it is important to continue evaluating and addressing the ethical, social, and environmental implications to ensure that these advances benefit society as a whole. Magnetism 6.1 Differentiating between magnetic and non-magnetic materials. When it comes to distinguishing between magnetic and non-magnetic materials, it is important to understand that magnetic materials are those that exhibit magnetic properties, while non-magnetic materials do not. Magnetic materials are capable of attracting or repelling other magnetic materials, whereas non-magnetic materials do not demonstrate such behavior. Some common examples of magnetic materials include iron, nickel, cobalt, and certain alloys like steel. On the other hand, materials such as wood, plastic, rubber, and glass are considered non-magnetic as they do not possess magnetic properties. 6.2 Explaining how a magnet can attract an unmagnetized object. The concept of magnetic attraction is fascinating. A magnet can attract an object that is not already magnetized by inducing a temporary magnetic field within the object. When a magnet is brought close to an unmagnetized object, the magnet's magnetic field interacts with the atomic or molecular structure of the object's material. This interaction aligns the unpaired electrons within the object, causing it to temporarily acquire magnetic properties and become attracted to the magnet. Once the magnet is removed, the object loses its induced magnetism and returns to its original non-magnetic state. 6.3 Distinguishing between materials used to make permanent and temporary magnets. Permanent magnets are made from materials that can retain their magnetic properties over time. These materials include steel and alloys such as alnico, aluminum, nickel, and cobalt, and rare earth magnets, neodymium and samarium cobalt. Permanent magnets are typically used in various applications, from industrial machinery to consumer electronics. Temporary magnets, on the other hand, are materials that can be easily magnetized but lose their magnetism when the magnetic field is removed. Common examples of temporary magnets are iron and certain alloys like mu metal. They can be magnetized by placing them in a strong external magnetic field, but their magnetism diminishes once the external field is removed. Temporary magnets are often used in applications where the magnetism needs to be switched on and off, such as in electromagnets used in scrapyards or magnetic locks. 6.4 Identifying the poles of a magnetic dipole. A magnetic dipole, such as a bar magnet, possesses two distinct poles known as the north pole and the south pole. The north pole of a magnet is attracted to the south pole of another magnet, while like poles repel each other. It is important to note that magnetic poles always occur in pairs, and they cannot exist independently. This means that if a magnet is divided into two pieces, each piece will still have a north pole and a south pole. Additionally, magnets align themselves with the Earth's magnetic field. The Earth's magnetic north pole is located near the geographic south pole, and the Earth's magnetic south pole is located near the geographic north pole. This alignment is why a freely suspended magnet will point towards the Earth's magnetic north pole. 6.5 Investigating the forces between magnetic poles. understanding the forces that exist between magnetic poles is essential in comprehending magnetism. The strength of the force between two magnetic poles depends on two factors: polarity and separation distance. Opposite poles, north and south, attract each other, while like poles, north and north, or south and south, repel each other. The force between two magnetic poles increases as the strength of the poles, measured in terms of magnetic field strength, increases. Additionally, the force decreases as the distance between the poles increases. This relationship follows an inverse square law, meaning that the force is inversely proportional to the square of the distance between the poles. Therefore, the closer the poles are, the stronger the magnetic force between them. 6.6. Defining a magnetic field. A magnetic field is a region in which a magnetic force can be observed. It is produced by a magnet or a current-carrying conductor and extends into the surrounding space. Magnetic fields are represented by magnetic field lines, which are imaginary lines used to visualize the direction and strength of the magnetic field. These field lines are drawn from the north pole of a magnet to its south pole, forming closed loops. The density of the magnetic field lines indicates the strength of the magnetic field at a particular point. The closer the field lines are to each other, the stronger the magnetic field in that region. Magnetic field lines never intersect, as this would imply the existence of multiple directions of the magnetic force at a single point. 6.7. Mapping magnetic fields. To map magnetic fields, various methods can be employed. One common technique involves using iron filings and plotting compasses. Iron filings align themselves along the magnetic field lines when sprinkled around a magnet. This arrangement gives a visual representation of the magnetic field's shape and direction. Plotting compasses can also be used to map magnetic fields. By placing a compass at different locations around a magnet, one can observe the compass needle's orientation. The needle aligns itself with the magnetic field lines, allowing for the mapping of the field's direction and strength. Furthermore, activities can be performed to map magnetic fields around a single magnet and between two magnets. These activities involve systematically moving the iron filings or compasses around the magnets to observe the patterns and changes in the magnetic field. By mapping magnetic fields, we gain a better understanding of their behavior and how they interact with different objects or magnets. Electromagnetism 7.1. Conducting experiments to investigate the magnetic field pattern around current-carrying conductors. In this topic, students are involved in conducting experiments to explore the magnetic field patterns generated by various types of current-carrying conductors. This includes experiments with straight conductors, flat coils, and solenoids. By observing and analyzing the magnetic field patterns, students can gain a better understanding of how the magnetic field is influenced by the current flowing through a conductor. 7.2. Applying rules that relate the direction of current flow to the direction of the magnetic field. Students learn about two important rules that help establish the relationship between the direction of current flow and the resulting magnetic field. The first rule is the right-hand grip rule, which allows students to determine the direction of the magnetic field by curling the fingers of the right hand around the current-carrying conductor with the thumb pointing in the direction of the current. The second rule is the right-hand screw rule, which helps students determine the direction of the magnetic field lines around a current-carrying solenoid. 7.3. Describing a commercial application of an electromagnet. In this topic, students study practical applications of electromagnets in commercial devices. They explore examples such as starter motors and magnetic relays, where electromagnets play a crucial role. By understanding these applications, students can see how the principles of electromagnetism are applied in real-life scenarios, contributing to various technological advancements. 7.4. Conducting an experiment to demonstrate the force on a current-carrying conductor placed in a magnetic field. Students engage in an experiment to observe and demonstrate the force experienced by a current-carrying conductor when placed in a magnetic field. This experiment allows students to directly witness the interaction between the magnetic field and the current, providing a hands-on understanding of the concept. 7.5. Sketching the resultant magnetic flux pattern when a current-carrying wire is placed perpendicular to a uniform magnetic field. In this topic, students learn to sketch the magnetic flux pattern that emerges when a wire carrying current is placed at a right angle to a uniform magnetic field. By visualizing and drawing these patterns, students can further enhance their understanding of how the magnetic field interacts with current-carrying conductors. 7.6. Applying Fleming's left-hand motor rule. Fleming's left-hand rule is introduced to students as a tool for predicting the outcome when current flows perpendicular to a uniform magnetic field. This rule is often applied in the context of motors, where the interaction between the magnetic field and the current results in mechanical motion. By using this rule, students can determine the direction of the force experienced by the conductor and understand its impact on motor operation. 7.7 Identifying the factors that affect the force on a current-carrying conductor in a magnetic field. In this topic, students learn that the force experienced by a current-carrying conductor in a magnetic field is influenced by two main factors: the strength of the magnetic field and the magnitude of the current. By understanding these factors, students can analyze and predict the resulting force on a conductor, enabling them to make informed observations and interpretations in related experiments and applications. 7.8 Explaining the action of a DC motor. Students gain an understanding of the basic operation of a direct current, DC, motor. They learn about the components and principles involved in converting electrical energy into mechanical motion. This knowledge provides students with insights into the functioning of motors and the application of electromagnetism in generating mechanical work. 7.9 Describing activities that demonstrate an induced electromotive force, EMF. Students participate in simple activities using coils and magnets to demonstrate the concept of induced electromotive force, EMF. By observing how changing magnetic fields induce currents in conductors, students can grasp the fundamental concept of electromagnetic induction and its practical applications. 7.10 Conducting experiments to determine the magnitude of the induced EMF. Students perform experiments aimed at investigating the factors that affect the magnitude of induced electromotive force, EMF. Particularly, they focus on studying the rate of change of magnetic flux experienced by a conductor. Through these experiments, students gain hands-on experience in quantifying and measuring the induced EMF, deepening their understanding of electromagnetic induction. 7.11 Predicting the direction of induced current given the direction of motion of the conductor and that of the magnetic field. In this topic, students learn to predict the direction of induced current in a conductor based on the relative motion between the conductor and the magnetic field. By considering factors such as the direction of motion and the magnetic field, students can apply their understanding of electromagnetic induction to determine the direction of the induced current. 7.12 Explaining the action of an AC generator. Students develop an understanding of the basic operation of an alternating current, AC, generator. They learn about the generation of alternating current through the rotation of a coil in a magnetic field. This knowledge helps students comprehend the principles behind AC generator operation and the conversion of mechanical energy into electrical energy through electromagnetic induction. Transformers. 7.13 Explaining the principle of operation of a transformer. A transformer operates on the principle of electromagnetic induction. When an alternating current, AC, flows through the primary coil of a transformer, it creates a changing magnetic field. This changing magnetic field induces a voltage in the secondary coil, which is connected to a load. The voltage induced in the secondary coil depends on the ratio of the number of turns in the primary coil to the number of turns in the secondary coil. Transformers are used to transfer electrical energy between different voltage levels efficiently. 7.1 For stating the advantages of using AC for transferring electrical energy. Using alternating current, AC, for transmitting electrical energy over long distances offers several advantages. Firstly, AC can be easily generated and transformed using transformers. This allows for efficient voltage transformation, enabling the use of high voltage for long-distance transmission, which reduces energy losses during transmission. Additionally, AC is less affected by resistive losses, making it more suitable for long-distance transmission compared to direct current, DC. The use of AC also allows for the use of three-phase power systems, which further improves efficiency in power generation and transmission. 7.15 Applying the ideal transformer formula. Pout equals pin. The ideal transformer formula, Pout equals pin, relates the output power, Pout, to the input power, pin, in a transformer. According to this formula, the power input to the primary coil of a transformer is equal to the power output from the secondary coil. In an ideal transformer, where there are no losses, the input power is equal to the output power. This formula is useful for solving problems related to power transfer in transformers. Transformer formulae to solve problems. VSVP equals NSNP equals IP is the provided formula. VSVP equals NSNP equals IP is a set of equations that describe the relationships between the voltage and current ratios and the number of turns in the primary and secondary coils of a transformer. VSVP represents the voltage ratio, which is equal to the ratio of the secondary voltage, Vs, to the primary voltage, Vp. Similarly, NSNP represents the turns ratio, which is the ratio of the number of turns in the secondary coil, Ns, to the number of turns in the primary coil, Np. Lastly, IP represents the current ratio, which is equal to the ratio of the primary current, Ip, to the secondary current, Is. These equations are useful for solving various problems related to transformers, such as determining the voltage or current in one coil when the other coil's voltage or current is known, given the turns ratio. They allow for calculations involving transformers, aiding in understanding and analyzing their operation and performance.